So in this session, I'm going to discuss on IB Chemistry Paper 2, which is done on 19 May 2025, and for the exam code of 22256209. So let's start for the first questions. In the first questions, it's asking to describe between the difference of an element and a compound. So an element is when it only contains one type of atom or atoms. So for example, if we have like sodium and A, it only one type of atom. How about fluorine gas? It's F2. There is two atoms on it, but then it's the same type, so it's also considered as an element. So element when it contains one type of atom or atoms with the same atomic number. What does it mean by same atomic number? So different elements will have their unique proton or atomic number. So element is basically if there is a more than one atom, like for example fluorine gas, there's two atoms, it need to be in the same atomic number, or essentially means that it need to be in the same type. How about compound? Compound basically is the opposite, contain two or more different type of atoms which need to be bonded together. So for example, if we have sodium chloride, it contains of Na and Cl, and they are bonded together, chemically bonded, so that's why they are considered as a compound. But then how about if in the one place we have iron and have cobalt, but they are separated? They are not chemically bonded, they only exist together. This is not considered as compound. Then we have another example like sodium sulfate, NaSO4. This is also considered a compound because there's Na, there's S and O. There's three different types of atoms. That's why this is also considered as a compound. Now we move on to the second question. The second question is asking, outline why solid iron sulfide is a polar covalent compound. If it's related to polar covalent, ionic, polar covalent, or non-polar, usually it will be related to electronegativity. So between the atoms in the compound, like here, iron sulfide is basically FeS. So between these two atoms, what is the difference in the electronegativity will affect how they bond together to form ionic, polar, or non-polar. So if we go section 9 and 17, which I have placed it here. So if you see here, 9 and 17, so 17 is the triangular bonding diagram. So this triangle bonding diagram shows that if you know the electronegativity difference and the average, we can map it out to know which is this compound stays. Is it in ionic area, or is it in the polar covalent, or is it in the covalent site? So we actually look through the electronegativity through this section 9 here. So let's zoom in more. We can see that the below part here represent the electronegativity, so we should see the one in below. So let's say the iron here, it is this iron here has a 1.8 electronegativity. How about sulfur? The sulfur has a 2.8. Okay, now we just need to move back to the electronegativity difference in the diagram. So here in delta x means that you want to know the difference between the largest electronegativity minus with the smaller one, which is here the larger one will be the sulfur, which is 2.8, minus with the one with the iron, which is 1.8, will become this sulfur is 2.6. That is 2.6, so it'll become 0.8. for the average electronegativity, this one will be equals to 2.6, and you adding up both the electronegativity, then you divide by 2 because there's two types, then you find the average. The average is 2.2. So if we map it out, it will be around here, 2.2 and 0.8 here, that you make a line. You can see that this is actually in the polar covalent area. So that's how you prove it. So when we are writing it down, you can say that based on the electronegativity difference, you got it as a 0.8, and then the average of the electronegativity is 2.2. And based on this, you can say that this shows this number shows that the compound is polar covalent through the mapping on the triangular bonding diagram. Okay. Alright, so we go for the next question. So the next question is asking, contrast one physical property of iron and iron sulfide. So we need to know the difference. So iron is a metal. Meanwhile, iron sulfide is a salt. So these two is a very different things, because an iron sulfide is a polar covalent compound, means it's a covalent bond. Meanwhile, for iron, it is a metal, so it's from metallic bonding. So the most obvious difference will be the electrical conductivity, electrical or thermal. And why is it so? So iron can conduct thermal or electricity. Meanwhile, FeS cannot conduct. Then why is the reason? It was because that in metal, if you remember, how does metal looks like? Let me draw it around here. So how does a metal looks like? Metal is basically, it's all positive ions. So it's because the electron can freely flowing around. So this electron is the one that bound all the positive ion of the iron together. This is called metallic bonding. The electron is flowing around. It's very easy to flow around from one side to other side. This is called as a Fe. So if let's say you put a thermal or you drive through the current, the electron can move from this side to the other side, So that's why it can conduct thermal or electricity. But then for FeS, it's a different thing. This is no longer a metallic bond where there's a free-flowing electrons. The Fe is bond with the sulfur, which means that the electron is tightly bound together, chemically bonded, and it's not free flowing around. So the electron cannot move from one side to the other side so easily. So this is the difference. Now we move on to the next questions. Calculate the wavelength in meter for the limit of convergence observed in the line spectrum of iron. Okay, it sounds very complicated. So basically, what does this mean is that line spectrum. So we focus on the what is the line spectrum of iron. So line spectrum of iron, if you all remember, there is a called things like N equals to 1, N equals to 2, and this is the energy level, or you can also say it's the shell number, so it's actually equivalent. People use it interchangeably. So you can say like the first shell, the second shell, the third shell, the fourth shell. So the energy level on this shell is actually, as it getting further away, the energy is getting closer and closer, where it converge. That's why it's called as a limit of convergence. It converges to a value where so when it's the n is infinity, means when the shell is very far away, like very far away, the energy is basically converge to a value, to this one value. When this n is equals to infinity, this is where the electron is considered as removed. Because it's too far, it's considered as removed. So that's why this limit of convergence is basically the energy level here. And people usually correspond it with the first, it corresponds as a first ionization energy. What is this first ionization energy? It's basically when the the outermost electron is being removed, which means that it's equivalent to like the electron is placed in this n equals to infinity. So in this limit of convergence level, there's energy there. There's energy which is, you can also correspond to the first ionization energy. The outermost electron that being removed to this n equals to infinity, basically removed very far away. And we want to know, then it's asking, what is the wavelength there? So we need to know the relation between wavelength and energy. So what in this energy here, what is the wavelength? So how do we know is that we can see the section 1, 2, and 9. So if we go up here, okay, if we go up here, 1, 2, and 9, here this is the section 1, 2, and 9. We want to know the correlation between the wavelength and the energy. So you can see that we have the energy here, and then we have the lambda here. So we can combine these two equations to form E equals to H. Then the F, we can substitute the F with this F, and it will become C over lambda. Then if we want to switch the E and lambda, we basically lambda is equals to Hc over the energy. And this energy is the, we know that from this H and C is a constant where we can find in the second physical constant here, which is the Planck constant and the speed of light. So the one that we need to know is only the energy. Okay, we need to know the energy. So we can pull down here first and we can write it down the formula just now. So we just write down the formula that we have before. Here it becomes lambda equals to Hc over E. And if we plug in the number just now, the constant of the Planck constant and the speed of light is 6.63 times 10 power of 34 times 3 times 10 power of 8 divide by the E, which we haven't know yet. This is the one that we're going to find. This energy is that, where is the energy that when the outermost electron is being removed to this n equals to infinity in this limit of convergence area. So how do we find the first ionization energy where this electron is being removed? Where is the energy we came from? This energy you can get from the Taylor paradox, because we know that this is for the iron. This spectrum is for the iron. So we can actually go and see the ionization energy in the chapter 9. So we can see the ionization energy is actually in the first ionization energy is in the top left corner. So it's at here. So it's at the area here, the top left corner. So if I find the iron, so the iron is here at the Fe here. So you can see this is 762. So this is the first ionization energy. But then you need to take note. If you see the unit here, this is actually kilojoule per mole, the unit. So it's 792 kilojoule per mole. But then the one that we want to know the energy is for one atom, that the electron. So when the electron is being removed, it's only for one atom. So we want to know one atom instead of the whole 1 mole. So we need to divide this energy with 1 mole, with the Avogadro constant. So what is Avogadro constant is also shown here. It's basically 6.02 times 10 power of 23. It basically means that how many atoms in this 1 mole. So we need to divide. So we know that the first ionization energy is basically equivalent to 762 kilojoule per mole. But we want to know the energy for one atom. So because of this, we take 762 kilojoule to joule will become 1000, become joule. Kilojoule to joule is times 1000, then divide by the number of Avogadro constant, which is just now is 6.022 times 10 power of 23. Then if we use the calculator, let's try 762,000 divided by 6.022 times 10 power of 23. So we got 1.266 times is 10 power of negative 18. So the answer is 1.266 times 10 power of negative 18. Okay, this is joule in terms of the joule per atom. This is now per atom instead of per mole. After that, we just place this energy to here. We just put this number to this energy here. It becomes 1.266 times 10 power of negative 18. Oh, this is power of negative 34. So I should modify this. So it should be 6.63 times 10 power of negative 34. The constant is supposed to be negative 34. Then you times it with 3 times power of 8. Then you divide it by 1.266 times 10 power of negative 18. And it is 1.571 times 10 power of negative 7. Let me write down properly. So it becomes 1.57 times 10 power of negative 7 meter. So this is the answer of the wavelength. So this is the wavelength.